Hey everyone, in this video we're going to cover bit shifts and rotations. Unfortunately, the Coombs lecture theatre seems to have some recording issues at the moment, and live coding demonstrations that I'm doing on my laptop aren't actually getting into the echo recording. So to rectify that, I'm making a couple short videos tonight. And this one's going to be on bit shifts and rotations. So what are our bit shifts and rotations? So first of all, if we go on our cheat sheet here, there's a nice section here under register moves. So this is on the first page, about 3/4 of the way down. Under register moves, we have shifts and rotates. So these are all the different shifts and rotates on your cheat sheet, and we're going to have a look at some of these. So some of them will take a constant, some of them will take a register, and as usual, you've got what you're operating on in your destination. Cool, so let's have a look at some practical examples and also have a look at what they do. Alright, so these first two are called logical shifts. Now, they're called a logical shift because they shift the bits and they fill with zeros. So logical shift left will move all of these bits to the left. The leftmost bit gets shoved into the carry flag if you have it set up to set flags, and then we'll fill in over here with zeros. So all the bits move left. This one gets dumped into the carry flag if you've done LSLC, and we fill with zeros. Logical shift right does the same thing, but the other way. So we take our bits, move them to the right. The first one over here gets shoved into the carry flag if we're doing LSRC. LSRS, excuse me. So if we do LSRS, that will get shoved into carry and will fill with zeros. Now, what's this shift here? This is an arithmetic shift right. So this is also a right shift, except instead of filling with zeros, we fill with whatever the most significant bit was, or the sign bit. So this will also shift to the right. If we are doing ASRS, this bit will go into the carry and will pad with whatever the sign bit was. Now we'll get to why this is useful to have later. Hint, it involves negative numbers and 2's complement. Our next shift is a rotate. So you can kind of think of this like if you wrap this register around into a circle and spin it around, you've got a rotate. So when it rotates to the right, everything that gets pushed off here gets tacked back on at the start. And if you're doing rotate right S, then the last thing to get shifted off will go into the carry flag. And lastly, we have RRX, which rotates right by 1, puts whatever it shifted off into the carry flag, and tacks the carry flag onto the end. This is called rotate right with extend. You probably won't use this, but it's on your board, so we're covered. Alright, time for some examples. Okay, so what do we have here? Here's one I cooked earlier. So at the start of the code, we're loading and moving some constant values into registers. You may be wondering what these load instructions are doing. Essentially what they are is just a move instruction for a big number. So if you ever have a number that's too big to fit into a move instruction, you can do LDR with an equal sign, and it's just like a move for a big number. Okay, so all of these are just moving numbers into registers. Now if you look over here, I'll just put these back in hex. So we have all of our numbers here are in our registers over here. Okay, so let's have a look at R0 first. So we're going to do a logical shift left on R0. We've got AAA, FF, FF in here, and we'll shift left by 4 places. And there we go. So now we have 3 A's and a 0 on the end. If I set this to a binary, you can see this is what our A's look like, 1, 0, 1, 0. This is what our F's look like. And we've got some zeros in here where we shifted to the left, and an A has fallen off into the trash bin over here. Now let's shift left a whole bunch more. There we go. Okay, So here we go, we've shifted left 26 places with a whole bunch of zeros in there, and we'll shift off the last little numbers here. And goodbye, my friend. It's nice knowing you. Okay, now let's do a logical shift right. I'll just set this to binary now so you can watch the numbers as they go. This is going to do the exact same thing, we're just moving it right. So here we go. A whole bunch of stuff just disappears off the end and we fill with zeros. Okay, now let's look at arithmetic shifts. You may remember from earlier lectures, if we've covered them. No, sorry, we haven't covered this, well, explicitly. So our numbers in binary, each binary bit, so we have 1, 2, 4, etc. So each binary bit has a value of 2 to the n, where n is however many number bits over it is. So let's say we had the binary number 1000 and we shifted it right once. Then we would end up with, so I'll just write this as a comment here. So let's say we had 100 in binary, and we shifted this to the right one place. So let's say we did an LSR of 1, and we'll just say this in imaginary register R0. Then we would get the result of this. I'll just put an extra leading 0 for brevity. So what have we done here? So this, excuse me, okay. So this bit position here, we've got the 1s column, the 2s, the 4s, and the 8s. So this is worth 8, this one. But now we've moved it over, well, we've got the 1, the 2, and the 4s column. So it's now worth 4. Now also keep shifting this over. It's now in the 2s column, and it's now in the 1s column. So you can see from this that every time we shift a number to the right, we're actually in effect doing a division by 2. So this works very well on a number like this, where let's just assume that this is a positive number that we're representing here, so we're representing positive 8. And there we go. Our logical shift works just fine for this because it places a 0 when it fills in. But what if we're trying to use a negative number, for example? So in my register 2 and 3 here, I've got negative 8. Now if we remember our 2's complement here, negative 8 is represented like this. So the useful trick is, I guess, is to flip all the bits and add 1. So this is what our negative 8 looks like in 2's complement. So we've got lots and lots and lots of 1s and a couple zeros here. So this is negative 8. So what happens when we do an arithmetic shift right? So because our first bit is set to 1, which we might call a sign bit, we know this is a negative number in 2's complement land. So when we do our arithmetic shift right, watch the number of zeros here. We lose some zeros, and we fill with 1s. So what we've in effect done is gone from negative 8, and we've divided by 2 twice, and now we have negative 2. And remember that all 1s in this would be negative 1, so this is negative 2. Now what happens when we do the same thing but with a logical shift? Oh no, we filled with zeros. So in 2's complement land, this is now a very big number. How big? Oh, huge. Well, if I set this to decimal, we've got half of that. So like half a million. So negative 8 just became 500,000. This isn't particularly useful when we're trying to do maths. So that's why the arithmetic shift right exists. If we're trying to do some shifts on a negative number in 2's complement, we can use arithmetic shift right, and everything behaves properly. Okay, that was a lot of information to take in. So you can just remember, essentially, arithmetic shift right, if you have a negative number, will make things behave the way you expect them to. Whereas logical shift right, you use for unsigned or non-2's complement represented numbers. Signed, arithmetic shift, unsigned, logical shift. And this is just for right shifts. For left shifting, you just use a logical left because it doesn't matter if it's signed or unsigned, they'll both behave properly. Alright, moving on. Let's go to our rotates. Okay, oh, I jumped the gun a little bit here. Okay. So register 4 did contain AA, BB, CC, DD, then I rotated it around. So a D dropped off the end and came around here. So we've gone from AA, BB, CC, DD to D, AA, BB, CC, D. Now, a question someone asked me at some point was, why is there not a rotate left? Well, remember that everything is going to wrap around, so we can do rotate lefts by rotating right a lot. Now, we're going to rotate right by 28 places. And this should be the same as rotating left by 4 places. There we go. So if you want to do a rotate left, then you rotate right by 32 minus however many places left you want to rotate. So there we go. So to rotate left, we rotate right, 32 minus the number of bits we want to rotate left. Okay, this concludes a little demonstration on doing rotates and shifts. If you have any further questions, please don't hesitate to ask your tutor or post on the Waddle forums. Thank you. Next video, we're going to look at loads and stores.